Okay, this lecture is on research designs, specifically experiments that have more than one independent variable. And this covers the first part of chapter 12 from the Morling textbook. So after hearing this lecture, you should be able to explain why researchers combine independent variables in a factorial design, be able to describe an interaction effect in both everyday terms as well as arithmetic terms, and then be able to identify and interpret the main effects and interactions from a factorial design. So to explain factorial designs and the concept of statistical interaction, I'll be using two examples in this lecture that are from the Morling chapter. And so in doing so, we'll start with just reviewing experiments that only have a single independent variable. So for example, take a look at this graph from a study by Duke and colleagues, 2011, that examined the effects of alcohol on aggression. They wanted to know basically whether people are more aggressive when they get drunk. So they had a placebo group drink orange juice with a very small amount of vodka in it, just enough to make them think that they were drinking alcohol, but not actually anything that would get them intoxicated. And then the alcohol group drank enough vodka to reach a 0.1 blood alcohol concentration. The participants played a computer game with an opponent who was actually in another room, or at least they thought they were actually playing against a computer. When the player made a mistake, the participant, they were able to give them an electrical shock as punishment. And so the researchers measured both the intensity as well as the duration of the shocks that were administered. Right here we've got a graph that shows the intensity of the shock. And what this graph shows is that the group of participants that were drunk administered more intense shocks. You can see the difference between those bars. So more intense shocks in the placebo group, all right? So that's just kind of a simple study, and I'll use that. We'll carry through that example or this example study throughout the lecture. Another example that was in the chapter was that not pictured here, but I'll draw on it, was a study by Strayer and Drews that was done in 2004 on the effect of using a cell phone while driving. Those researchers had participants talk on a hands-free cell phone while driving in a realistic driving simulator. So they weren't actually out on the road doing it. It was a driving simulator, okay? And so part of the time they had a conversation on the phone with the research assistant, and for other driving segments, they were not on the phone. And that was counterbalanced, but anyway, that's a detail. And then one of the dependent variables was just to see their reaction time, so how many milliseconds it took for them to start braking when they were required to brake by the driving simulation. Okay. Now, in this particular study, there's just a single independent variable, whether or not they were driving while talking on the cell phone. The overall result here was that when drivers used the hands-free cell phone, they were slower to hit the brakes than when not talking on the phone. Exactly what you would think. Okay. Now, for both of these studies, the effect of drinking or being drunk on aggression, the second study, the effect of using a cell phone while driving on one's braking time, we can ask whether these overall results depended on any other variables. So for example, in the alcohol and aggression group, we might ask, we've just got a placebo group and a drunk group, but we know that alcohol affects people differently. We also know that people have different predispositions or tendencies towards aggression. So for example, do we think that this overall result would hold for both men and women? Okay, we could ask, does participant gender play a role here? Does that matter? Do these effects that we're looking at, do they depend on gender? What about aggressive disposition, as if, for example, alcohol tolerance as another example? In the driving study, looking at cell phone use and braking time. Well, reaction time would seem to have something to do with one's age, as a for example. So very old people tend to have not as great of reaction time as teenagers, as a for example. So would using a cell phone, that overall effect that using a cell phone increases braking time, is that true for teenagers as well as very old people? Or does age, do the results depend on age? Maybe you don't get the effect for young people. Okay, there's also comfort with cell phones and technology. Younger people tend to be more comfortable. Maybe they're used to driving. Unfortunately, maybe they're used to driving with the cell phone and their reaction time is really not impaired or affected because of practice. It's the only way that they've ever learned, that some folks have ever learned how to drive, unfortunately, is with a cell phone present. Okay, so in both situations, though, we're asking whether the overall result depends on other variables or other factors. So when we're asking these questions, we're really getting at the idea of an interaction effect. Okay, we're wondering whether the overall effect of the study of the single IV depends on other factors or other variables. This is known as an interaction effect, or just an interaction. And this occurs when the effect of one independent variable depends on the level of another independent variable. An interaction between two IVs, or independent variables, allows researchers to determine whether the effect of one IV depends on the level of another. Okay, so let's consider the two previous studies. So the difference in the intensity of the shock delivered between the placebo group and the drunk group could depend on participant gender. So we might see that the difference in the intensity from the placebo group to the drunk group could be even greater for men than women. Okay, so maybe overall women don't give very intense shocks. They're not very aggressive, and that's the case whether they're drunk or not. They're just less aggressive. However, for men, we do see a big difference. Okay, that when men get drunk, this is a hypothetical, by the way, that I believe would be consistent with psychological research, but just as a hypothetical in this case, that men when drunk would give a shock of greater intensity. Okay, another example. Okay, maybe the difference in reaction time between driving with a cell phone or not depends on age. Again, the difference in reaction time could be even greater for older people than for younger people. So among younger people, maybe we don't see much of a difference in reaction time, regardless of whether they have a cell phone or not. But for old people, that cell phone really impairs their driving, and they have a much slower braking time with a cell phone than without a cell phone. Okay, so this is what we're getting at with interaction effects. Now, to help understand interactions, I think it is useful to just review what Morling in the textbook talks about as intuitive interactions, just to understand the concept. So one type of interaction that is graphed here is called a crossover interaction. I think you can see why it's called a crossover interaction because of the shape that the graph takes. This is really meant to show that the effect of one variable depends on the other. So for example, we could ask, does the temperature at which food is served affect how much we like it? The answer, of course, is that it depends on the type of food. We tend to like to eat our pancakes hot, but not cold. And we tend to like our ice cream cold and not hot. Okay, hot ice cream, that's disgusting. Just a bowl of hot soup, like gross. Okay, it's not ice cream anymore. So really, we can't say that we have an overall preference for food that's being served hot or cold. The effect of temperature on our liking depends on the type of food. So it depends. The effect of how the food is served, cold or hot, depends on the type of food. Here's another type of interaction. This is known as a spreading interaction. Take a look at the graph. Okay, so the name kind of implies the shape or the form of the graph. So in this example, just very simple and intuitive example, the pattern here could be described with the phrase only when. Okay, so my dog sits when I say sit, but only when I'm holding a treat. Okay. So what we have here is this is the proportion of the time that the dog sits. We'll just say that this orange bar is when you don't have a treat. And when you say nothing or whether you say sit, if you don't have a treat, that dog is not sitting down. We'll just call it 0, okay? The dog is not sitting, okay? So your dog only sits, it sits only when you're holding a treat, okay? If you don't have a treat, it doesn't sit. It sits only when you're holding a treat. So that's known as a spreading interaction. This is just to show that you can take that same data and you can graph it in a slightly different way. Okay, so previously the lines were whether or not you're holding a treat. Here the lines represent what you say, either saying nothing or saying sit. You'll notice it's the exact same effect, it's the exact same pattern of data, but it's just graphed differently. Okay, here the two different categories are holding a treat versus not. Previously it was say nothing versus say sit. So you can always graph an interaction in multiple ways. It just depends which way is more clear or you think will be more intuitive to the audience that you're trying to communicate the result to. All right, so research designs that have more than one independent variable are known as factorial designs. In factorial designs, the independent variables are called factors. What we have here is a depiction of the study that examined the effect of talking on the cell phone and driving performance, so braking or getting in accidents. But here, we're seeing whether the effect of the cell phone depends on driver's age. So we've got one independent variable or factor, which is whether or not we're driving on the cell phone or not on the cell phone. And then we're going to cross this design with another variable, another factor, which is age. And so doing so, by crossing one variable with two levels and a second variable with two levels, we get a 4-variable design. Younger variables on cell phones versus not, older variables on cell phones versus not. Okay, so in order to determine the number of conditions, the number of unique conditions in a factorial design, it's a simple matter of multiplying the number of levels of the first independent variable by the number of levels of the second independent variable. So here we've got a 2 by 2 design yields 4 cells or conditions. Okay, so cells is just a terminology for conditions in a factorial design. A couple other things just in terms of key terms. So we've got cells being the conditions in a factorial designs. We also have in this particular study both manipulated variables as well as participant variables. You might have noticed that in the study, cell phone use is a manipulated variable, okay, because the researchers were able to manipulate whether or not participants drove with a cell phone. But age is not a manipulated variable because people can't be randomly assigned to age. It can't be manipulated. Rather, age is a participant variable. A participant variable is treated as an IV or as a factor in a factorial design, but it's important just to distinguish. You can have what a manipulated variable is. It's actually manipulated. You can randomly assign people to different treatment levels and control the amount or the extent of the level of that independent variable that people receive. Alternatively, with a participant variable, we're talking about a naturally occurring variable. All right, so why do researchers use factorial designs? Several reasons. One is to test limits. So the idea is, with a factorial design is you can test whether an independent variable affects different kinds of people in the same way or differently. So the cell phone study is a good example. By looking at the combination of cell phone use and age, researchers are asking the question of whether the effect of cell phone use is limited to one age group or whether it would have the same effect regardless of people's age. Okay, so they can ask, hey, does using a cell phone, does that really, does that only affect older people? Is it limited to older people, or does it apply more generally? What we can see from the numbers, and I think it's easier to pick out the results using the graph, is that you'll notice in the graph that the two lines are parallel. And so the lighter blue is older drivers, the darker blue is younger drivers, and then we've got our two different conditions on a cell phone, not on a cell phone. What you can see is that the effect of talking on the phone did not depend on age. It is true that older drivers brake more slowly. Okay, their braking onset time is 1100 milliseconds as compared, or thereabouts, between 1000 and 1100 compared to 800 and 900 for younger drivers. But you'll notice that there's a consistent effect of being on the cell phone, that increases braking time in a consistent way for both younger or old. Okay, so age is associated with braking. Using a cell phone is associated with braking, but we can't say that that there's a limit to the effect of cell phone based on age. There's no interaction between the two. Okay, here's another idea, the idea of testing limits. You might recognize the goal of testing limits as being related to external validity, the external validity of the study. Essentially what we're asking is, does the effect generalize to other people, to other situations, to other conditions? So testing limits really relates to testing the external validity of a phenomenon. So going back to the alcohol and aggression study, what if researchers wondered if the effect of alcohol on aggression depends on body weight? So researchers actually did this. They randomly assigned men to a drunk group and a placebo group, measured their aggression through shock intensity during the game. But then what they did is they segmented the participants into light men and heavy men. And so what you can see by looking at the graph is that the effect of alcohol was stronger actually for heavier men, which is counterintuitive to me, but I guess that's what they found. I would think that alcohol would affect the light men more, right? It's like they likely have less of a tolerance to the alcohol because of their lower body weight. But for whatever reason, you see that there's an effect of drinking the alcohol. If we look at the bars for light men, we've got a smaller effect, right, where they are delivering a higher intensity of shock when they're drunk. But for heavy men, you really get that effect. Okay, look at the increase from the placebo group to the drunk group. So there's a stronger effect of being drunk on aggression for heavy men than there is for light men. So we can talk about moderator variables, and this is a concept that has been in previous lectures, but we'll return to it. Is a moderator is a variable that changes or affects the relationship between another IV and a dependent variable. And we say that the effect of the IV on the DV is moderated or depends on the level of another variable. Okay? So what we would say here is that the effect of alcohol on aggression depends on a man's body weight. That body weight is a moderator of the relationship between alcohol and aggression, such that there is a stronger positive relationship between alcohol and aggression for heavier men than there is for light men. All right. Why else do researchers use factorial designs? It's to test theories. So it's not just about the generalizability, okay? of a causal variable for external validity purposes, but rather to test theories. Many theories make predictions about how variables might interact with another, and factorial designs are a good way to test an interaction to see if the results are consistent with your theory. So according to certain psychological theories, there are boundary conditions. We expect the phenomena to happen under one set of conditions, but not another. So it's a way to test those theories. All right, so when reading a research article, it's important to be able to pick out and interpret the results of factorial designs. And a factorial design will have effects that are called main effects, and then of course we'll have an interaction, which is what we've been discussing. So we're going to go over how to determine what main effects are, what interactions are, and then be able to pick out the possible main effects and interactions using really the simplest version of a factorial design, which is a 2x2 factorial design. Okay? And so when we see this notation, we're talking about we've got two different independent variables, and there are two levels of each variable. So all the examples that we've been talking about so far with alcohol, body weight, and aggression. Okay, we've got alcohol intake, placebo group versus the drug group, and then body weight, heavy versus light. Okay, two variables, two levels. Cell phone and age. First variable, cell phone use. They either strove with a cell phone or not, two levels. Age, segmented into two different groups, the old group and the young group. Okay, so that's the simplest version of the factorial design, and that's how we're going to be introduced to the concept of main effects and interactions. These principles hold in more complicated designs as well. Okay, so in a factorial design, when there's two variables, we can have two main effects for each of the variable. So main effect is whether there's an overall effect of one of our IVs on the DV averaging over levels of the other IV. Okay, it identifies a simple difference. So with two independent variables, there's two main effects. So in our example here, we've got our driving using a cell phone and then driving performance. And here the dependent variable is no longer braking time, but it's the number of accidents. So in this 2x2 factorial design, we've got a first variable, which is whether or not we're driving with a cell phone, so cell phone use, and we've got a second variable, which is age. So what we can ask is whether there is a main effect for age and whether there's a main effect for cell phone use. Okay? And we do that by examining something called the marginal means. Okay? The marginal means we get by taking the average across the two different cells at one level of one of the independent variables. So if we want to get the marginal mean for young drivers, that is the number of accidents that young drivers had, okay, on average across both the cell phone and the not cell phone condition, we simply take the average of 10 and 4. 10 plus 4 is 14, divided by 2 is 7. Okay? So 7 is the average of 10 and 4, and we do that for older drivers as well. Okay? So if we want to ask if there's a main effect of age, we're going to compare the marginal means to see whether they're different. And in doing so, we see that on average, young drivers had 7 accidents. On average, older drivers had 7 accidents. So there is no main effect of age because there's no difference. What about for cell phone use? We're going to do the same thing. We're going to average across the levels of the other variable. Okay? So we're going to average 10, which is the cell mean for young drivers. We're going to average that with 10, which is the cell mean for older drivers when talking on the cell phone. The average of 10 and 10 is 10. Same thing for not on a cell phone. The average for young drivers is 4. Average for older drivers is 4. Average those two together, we get 4. So what we're going to say is that there is a main effect for cell phone use because the number of accidents is different. And by the way, right now we're not going to really worry about is there a statistical significant difference or not. We're just going to say if the numbers are different, for the time being, we'll treat them as being statistically significant. Okay. So we see that we've got two possibilities for main effects. We can have a main effect of age. There wasn't. We can have a main effect for cell phone use. There was. Okay, and it's possible to see this in the graph as well. This graph very nicely illustrates that there's a main effect for cell phone use, but because these two bars, these two lines are identical, we see that there's no main effect for age. They're identical. Okay. What about an interaction? Well, an interaction is going by asking whether there's an interaction, we're asking whether the effect of one independent variable depends on or differs at the levels of the other variable. Okay, so the way that we're going to look at that is we're going to look at our overall effect. Our overall effect, looking at the marginal means, is to say that ignoring our participants' age for the time being, on average, participants had 10 accidents when on the cell phone and 4 accidents when not on the cell phone. And then we're going to say, is that consistent for both of our groups of drivers, or does it depend? Well, we can see very clearly that we get that exact same consistent effect regardless of whether we're talking about younger drivers or older drivers. So what we can say is that the effect of using a cell phone, which is to have 10 accidents versus 4, does not depend on driver age. Therefore, there is no interaction. Those two variables do not interact with one another. We could actually look at that. We could see whether there's an interaction by looking at the null effect as well, actually. Okay, we can say, is there a difference between younger and older drivers in terms of the number of accidents that they get into? Well, on average, they get into 7 and 7. Okay, that's on average. But we see that there's no difference between young and old. Is that true when on a cell phone? Well, yeah, they get into more accidents when on the cell phone, but there's no difference between the two age groups. Same here, when they're not on a cell phone, they get in fewer accidents, but there's no difference between the two. So this main effect of no difference holds at both levels of cell phone usage. Okay, so that's just another way. We basically just kind of doubled down on our explanation. We knew that there wasn't an interaction, but we just showed in a second way that there was not an interaction between those two variables. All right. Here's just a different way to graph. It's the exact same data, but all we're doing is just displaying the data differently and graphing it in a different way. And the way that you graph it is really a choice. If your goal here is to show the main effect for cell phone use, this graph does it, I'd say, much nicer. You can see very clearly for both groups of drivers the main effect of cell phone usage. Okay. Oh, I'm so sorry. I said that there was. It's the same data. It's not. Just disregard. Okay. What we have here is we have a main effect for age, but not for cell phone. Okay. We have a main effect for age, but not cell phone. So here we're seeing that on average, younger drivers get in more accidents than older drivers. Seems about right, by the way. And then what we see here, though, is that being on a cell phone doesn't seem to affect accident rate. So whether or not people drive on a cell phone versus not, on average, they're getting in a similar amount of accidents. Okay, you can see very clearly from the graph, younger drivers get in more accidents than older drivers. Okay, so there's a main effect. And we can, again, is there an interaction? We can say, does the main effect of age seem to depend on cell phone use? Well, no, not really. We've got these parallel lines. So we've got younger drivers consistently making 6 more accidents than older drivers, and that's regardless of whether they're on the cell phone or not. Okay, so this main effect where younger drivers are getting in 6 more accidents than older drivers on average, it holds true whether they're on the cell phone versus not. Okay, so here we have a main effect for age, no main effect for cell phone, and no interaction. There's a main effect for age, and that's it. Okay, what about this? This is an interesting one. This is an example of an interaction, and we can really spot this by saying one way to detect an interaction is to say, is there a difference in the differences? Okay, so both the table and the graph show an interaction between cell phone use and driver age. Interestingly, there's no main effect for age and there's no main effect for cell phone use, but there's very clearly an interaction. Why? Because whether or not young versus old drivers engage in more accidents depends on whether they use a cell phone or not. So we can say, who gets in more accidents, younger drivers or older drivers? Well, it depends on whether they're using the cell phone or not. When on a cell phone, younger drivers get in 6 more accidents than older drivers. But that pattern reverses exactly when they're not on a cell phone, such that older drivers get in 6 more accidents than younger drivers when they're not on a cell phone. Okay, interesting. So maybe because older drivers know, their vulnerability, they're just a lot more careful. That might explain why they drive like 55 miles an hour on the highway. So talking on the cell phone, they're being very cautious. Young drivers are not. They're not moderating their behavior. But then, of course, not on a cell phone. It's like older drivers are maybe not as vigilant as they should be. Anyway, making up why we get the pattern. Doesn't really matter. Let's just understand the pattern, okay? So what we're looking here is that there's a difference in the differences, okay? On the cell phone, we get a difference such that young drivers 6 more, but not on a cell phone difference such that young drivers 6 less, 6 fewer accidents. So we can say that the difference in the number of accidents between those that were using versus not using a cell phone depends on driver's age, okay? What about this pattern of data? Take a look at it for a minute. Okay, recall that there's 3 effects. There can be a main effect for cell phone use, there can be a main effect for driver's age, and there can be an interaction between cell phone use and driver's age. The thing that we're going to do to look for the main effect of cell phone use is we're going to look at the marginal means, and we're going to look at those marginal means and see whether they're the same or different. Okay, so here's our cell phone variable, on the cell phone versus not, marginal means in yellow, 5 versus 5, not different. So the marginal means are the same, so we say that there is no main effect for cell phone use. Overall, on average, cell phone use doesn't make a difference. What about for driver's age? We're going to look at the marginal means. And again, just to recap where these marginal means come from, it's the overall average of accidents for young drivers collapsing across or averaging across the 2 different experimental conditions, the 2 different cell phone conditions. So the average of 8 and 5 is 6.5. For older drivers, the average of 2 and 5 is 3.5. So is there a main effect for driver's age? Yes, there is, because we say on average, younger drivers get in 3 more accidents than the older drivers. Okay, those marginal means are different. There is a main effect. What about an interaction between cell phone use and driver age? Well, one way to look at this is to say, all right, so on average, there's a main effect for age such that young drivers get in 3 more accidents than older drivers. Is that difference of 3 consistent across the 2 different cell phone conditions, or is there a difference in the differences? Okay. Well, what about on a cell phone? There's a difference of 6. Younger drivers get in 6 more accidents than older drivers. What about not on a cell phone? The difference is 0. So there's a difference in the differences. The difference is 6, the difference is 0. A difference in the differences. So the reason that we have this overall effect of younger drivers on average get in 3 more is because we're looking at a difference of 6 here and a difference of 0 here. So it averages out to 3. But the pattern is really that we get this big effect in the cell phone condition such that young drivers get in more accidents than older drivers, but that doesn't happen when not on a cell phone. Okay, and so that's graphed here, and this is one of these kind of spreading activation graphs. So we have a main effect for age as well as an interaction, because this main effect it depends on the level. Okay, the effect of age really depends on cell phone usage. There's not a consistent effect of age. Okay, what about here? Main effect for cell phone use. Okay, we're going to investigate the marginal means. The main effect for driver's age, we're going to investigate the marginal means, and then an interaction effect between cell phone use and driver's age. Let's do the first one, main effect for cell phone use, compare the marginal means. Definitely different. So yes, we have a main effect. What's the nature of that main effect? When talking on a cell phone, on average, drivers get in more accidents than when not on a phone. Okay, so forget about the age for a minute. We'll just make the general statement: drivers get in more accidents when talking on a cell phone versus not. What about, is there a main effect for driver's age? Yes, there is. 5 versus 7. So we'll say overall, on average, ignoring for a moment whether people are talking on the cell phone versus not, older drivers get in more accidents than younger drivers. Is there an interaction? We can look at this in a couple different ways. Let's look at it. Let's look at it this way. We're going to ask whether the effect of talking on a cell phone is consistent for young drivers and old drivers. So what's the overall effect? It's a difference between 10 and 2.5. So drivers on average get in 7.5 more accidents on the cell phone versus not. Is there a consistent 7.5 difference for both young drivers and old drivers? So what we're going to be looking for young drivers as well as old drivers, is there a consistent difference of 7.5? Well, what's the difference here? The difference between 8 and 2 is 6. And the difference between 12 and 3 is 9. So there's not a consistent difference. Okay, so young drivers, we can say that the cell phone doesn't affect them quite as much. They get in 6 more accidents. Older drivers, the cell phone seems to affect them more. They get in 9 more accidents. So this average of 7.5 is really found between taking, a difference of 6 accidents versus a difference of 9 accidents. Okay, and that's graphed over here. As you've got older drivers are the light blue, younger drivers are the dark blue. What we can see is that for both older and younger drivers, there's an increase in accidents. There's more accidents when talking on the cell phone, but there's a stronger effect. There's a stronger effect of the cell phone for older drivers than younger drivers. So the effect of the cell phone depends on age. You get a stronger effect of using a cell phone for older drivers versus younger drivers. Okay. So it is useful to use graphs in order to spot interactions. And so I find it's much easier to detect interactions from a graph than computing them from a table of means. If the results are plotted in a line graph, as it is with these top 2 graphs, one thing that you can do is just look to see if the lines are parallel. In the graph on the top left, the lines are not parallel, they're crossing over. So there is an interaction. Okay, so anytime the lines are not parallel and will intersect somewhere in space, you've got an interaction. Okay, and the graph on the right, the lines are close to parallel. Okay, if they're perfectly parallel, no interaction. We're just say that the lines here are close to parallel, so there probably is no interaction between cell phone condition and age. In both cases, of course, you would actually need to perform a statistical analysis to see if there is a statistically significant interaction effect. But just visually, in looking at graphs, I would say, yes, there's bound to be an interaction here, versus no, there's probably not here. We can do this with the bar graph as well. Let's go to the example where there's not going to be an interaction. And again, what kind of the phrase to have in your head is there a difference in the differences? Is there a difference in the differences? Well, let's just look at young drivers are the pink bar, old drivers are the orange bar. We can see that there's a difference here. I won't do the numbers. It's about that big. And it looks like that's about the same amount of difference in not on a cell phone condition here. So those differences look to be about the same. In other words, we got older drivers that are slower to brake, and they're slower regardless whether they're on the cell phone or not on the cell phone. Okay, so we don't see an interaction there between age and cell phone usage on breaking time. Here, what if the pattern was this reaction time? Slightly different example. I forget what this example was, to tell you the truth. We got alcohol photo and plant photo. Doesn't matter. But again, looking to say, is there a difference between the differences? Here we've got neutral words resulting in a longer reaction time than aggression-related words, but the pattern flips when looking at plant photos. Who knows what this study was? Forget. Such that now the pink bar is higher than the orange bar. Okay, so this is this crossover pattern. And in a way that you can kind of in your mind is you can produce the line graph by just connecting the top of the graphs. Okay, so this pink line you'd get if you just connected the top of these bars, and this orange line you'd get if you connected the top of the orange. Same thing, you get these parallel lines by connecting the tops of the bar graphs. So when parallel, no interaction. When intersecting lines, there is an interaction. So intersecting lines, interaction. When describing an interaction in words, you should start with one level of the IV and then explain what is happening with the second IV at that level. And then you move to the next level of the IV and do the same thing. So this approach is depicted in the two graphs here, and then here's some language that the textbook author gives us. So here we've got a number of items recalled. We've got a study with chess experts, child chess experts versus novices. And if we're trying to say, we've clearly got an interaction here, and to describe the number of items recalled, we would have to say that recall for chess pieces versus digits depends on whether we're talking about child chess experts versus adult novices, such that child chess experts can remember more chess pieces than digits. Okay, here's the child chess experts. They remember more chess pieces than digits. But adult chess novices can remember more digits than chess pieces. So that's one way to describe it. Here's another way. This was the alcohol, aggression, and body weight. The drunk group was more aggressive than the placebo group, and this was especially true for heavy men. That's a way to describe the interaction in words. The textbook author makes the point, and I think I agree, that interactions are more important than main effects. So when a study shows both a main effect and an interaction, the interaction is almost always more important. So there might be real differences between those marginal means, so there might be a main effect, but the more exciting part is the interaction. And chances are when you see a factorial design in the research, you see a published design that is a factorial design, chances are the researcher is looking for an interaction in the first place, and that's why they have a factorial design. So that's usually the purpose of the study. And in many ways, the interaction is more important because it kind of qualifies any main effect that is found. So if you find that there's a difference in the number of accidents that people get into when talking on a cell phone versus not, you really have to say yes, but you definitely see that, and it's a much stronger pattern among older versus younger drivers, as a for example. So the interaction kind of puts those boundary conditions or qualifiers around the main effect. All right, and so the remaining slides are just a review of all the different possibilities and of effects that you can get in a 2x2 design. And so recall that you can have a main effect for one variable, a main effect for the second variable, and an interaction. And so here we've just got the cell phone use, driver's age, and this table goes through all the different examples. So it's possible to have no effects. It's possible to have all three effects present, it's possible to have all different combinations. And so these slides essentially just go through those different combinations, and it's worth reviewing to make sure that you understand all those different possibilities and combinations to be able to pick them out of a research article, or to be able to identify whether there's main effects or interactions and what combinations on, for example, a test that you might get in your research methods class. So that's it for this lecture. Hopefully you've enjoyed learning about factorial designs and know more about why they're conducted, as well as would have the ability to pick out main effects and interactions in a research article.